Finally, it's an honor to have this afternoon Brent Tully, Emeritus Professor at the University of Hawaii, with us, joining us for the NIRCam colloquium. Brent, I'm sure you know him, he doesn't really need a presentation, but it's our habit to have a presentation. We have a very broad community going from people working on technology to stellar astrophysics. So Brent is originally from Canada, and he got his PhD at University of Maryland after several postdocs, including Europe. In 1975, he joined the faculty of the University of Hawaii and has remained there ever since. And in 1977, Brent, along with J.R. Fisher, he discovered a way to measure distances to galaxies through the link between circular velocity of galaxies and their intrinsic luminosity. This is the so-called luminosity line relation, which is popularized as the Tully-Fisher relation, which is now used as the standard tool for cosmology. I know that Brent, has been done way more than that. He's been working a lot on many different fields of astrophysics, and for his work, in particular for his contribution in cosmology and for the local universe, Brent received several awards, including the Gruber Cosmology Prize, the Wempe Award, the Victoria Ambartsian International Prize. And again, thank you for being here today, talking about our population to TRGB-SBF route to the Hubble constant with HST and Jimmy's web. Give you the floor, and I'll tell you when you have time.
Thanks, Mickey, and thanks for having me here. I have to apologize right up front that my hearing is really quite bad, really bad. In fact, you can see it here. I've got a connection to my brain directly with a cochlear implant. I just got it a couple of months ago. And I might, if you're asking me a question, I might actually stick a microphone in your face here to correct my ear. Anyways, the story that I wanted to talk about today, I prepared it because there was a meeting in Porto a couple of weeks ago celebrating, it was the Hubble Space Telescope and James Webb Space Telescope. They brought together people who have been using those telescopes and just to have a fest about it. And certainly what we've been doing was worthy of discussion there. And I'll talk about it here today. Let's see. Oh, I had this device over here. Yeah, so here's the people that have been working with Gabriella and Michele are involved in this. Anand has been doing the tip of the red giant wedge work, and John Blakesley and Joe Jensen have been involved in surface brightness fluctuations. And so that's these are the characters that are involved. Let's see, do I have to point it at something? Why am I not going in? So, if you've been not sleeping under a rock, you probably have heard that there is a Hubble tension. This is then the fact that different values for the Hubble constant are coming from theoretical models of how the originating out of information from the CMB information in the early universe, and a model of how the universe evolves from that time till the present day. And if we understand that, this lambda CDM model that's popular, then Hubble constant is 67. I made a very small error bar on that, like ±1. And meanwhile, people have been using the ladder in various other ways. The ladder being, there's no good way to measure distances both nearby where you can get a 0-point calibration and at the far field where you're not bothered by peculiar velocities with one method. And so the latter is this using a sequence of methodologies. And the most popular one, or the one that's really gotten the most press, is the work done by Adam Rees, who uses a ladder that, no, I'm going to use this pointer here. It involves 3 steps. First step is using geometric calibrations of parallax information to get a 0 point on Cepheids. Then doing a link between the Cepheids and supernova, type 1 supernova, where these are in galaxies where you can actually measure Cepheids at the same time as the supernova's gone on in that galaxy. And then using supernova at large distances where the peculiar velocities are not disturbing the Hubble flow particularly. And this population 1 ladder then has given a value of the Hubble constant of about 73 with an error of a couple. But the difference between then that 73 and the 67 is nominally about a 5 sigma effect. The implication then is if there's no mess up on either of the 2 calculations or observations, then there's something wrong with the model of the universe. And that's why this is important, because there's physics that we don't understand in the model of the universe, which is pretty fundamental. So, but what do we do? What can be done though? 5 sigma sounds pretty great, but maybe there's systematics, maybe there's hidden systematics. So what would be nice then is to have a population, a totally independent methodology, no overlap. And that's what we're going to talk about today, no overlap. It's a population 2 ladder, population 1 on the other case, because Cepheids only are young stars, and so they only happen in star-forming galaxies, and the supernova then that they're calibrating are all supernova in young galaxies. So this is a population 1 ladder all the way up, because the first steps then you're calibrating distances with Gaia or whatever to get good calibration on the Cepheids. And now we're going to substitute in here, substitute Cepheids. We're going to talk about tip of the red giant branch, which is population 2 star. We're going to transfer that across the surface brightness fluctuations, which is again a population 2 population. And then at the large redshifts, we're using surface brightness fluctuation. So we go all the way up the ladder in 3 steps, same 3 steps, but now replacing all of the elements with population 2 features. And so entirely independent of the population 1 scale. And we're using then for TRGB, using these filters with HST and James Webb telescope, and then in surface brightness fluctuations, again, we're using F150 W 1.5 micron filter with both HST and JWST. Okay, just to remind us, tip of the red giant branch, here's just a color magnitude diagram obtained with Hubble Space Telescope of the Phoenix dwarf galaxy in the local group. And you see the tip of the red giant branch here. Other features that you see here are the horizontal branch, not horizontal in these filters, but okay, horizontal if you're in the high and the V band. And along that way, along that branch are Lyrae stars. And so this is an example that the tip being very well defined. Here's just a potpourri of TRGB observations on local group galaxies, and it's not complete. I just put as many as I could on this page here, and you can always, you see in every one of these local group galaxies that the red giant branch is well formed and going up to a well-defined tip. And now with JWST, data is starting to come in of this kind of quality for these local group galaxies. This is a local group galaxy at a little bit less than 1 megaparsec away. And here's the beautiful data that you get with JWST. And you can see not only the tip, you see the horizontal branch here, red clump, and this is, of course, the main sequence. And cepheids would be up here. And now these are not all reduced, they're not all in, but all of these local group galaxies are being observed. And so come back in another year or so, and you're going to see, we're essentially, well, for most of the local group galaxies, you're going to be seeing data that's of this quality. And again, all of these cases, we're going to be easily seeing the RR Lyrae stars in the horizontal branch. And so we'll be seeing both the tip and the RR Lyrae stars. And that difference then, so one of the big issues then that I'm not involved in, but what I'm trying to learn as I come to Europe here is, in fact, how well do we know the horizontal branch RR Lyrae luminosities? They've got metallicity issues and stuff, but we're seeing thousands of them with Gaia, and so I'm really expecting then that in the you know, there are issues with Gaia, but I'm sure they're going to be resolved. And so one of the things that we will know very well is this step here, and we'll know the 0 point from Gaia information on local RR Lyrae stars. Now, I might overuse this word Rosetta Stone because I'll use it twice, but this galaxy NGC 4258, which is about 7.5 megaparsecs away, is a remarkable gift to astronomy. It is a almost edge on, well, in the inner part, it's got a black hole with a almost edge on rotating disk, which has maser features, and the maser and gas is rotating around the black hole in essentially Keplerian orbits, and so there are maser features in the gas, both coming toward us and away from us, and going across the line of sight in the nuclear region. And from that geometry, beautiful geometry, lucky geometry, we're able to get a distance measurement, which is geometric, if you like, of this high accuracy here, which is 1%. I'd like to point out that there's not a second case like this anywhere nearby. There's another half a dozen or so galaxies that have maser work done on them, but the geometry isn't as nice. The masers aren't as strong. They're farther away in the errors are large. It was a real gift that we had this wonderful galaxy so close to us. Anyways, we can then use, I call it a Rosetta Stone because there's all these other ways of getting distances to it as well. For example, Adam Rees is using it to get cepheid distances. Here's some observations. So it's been observed both with HST and JWST abundantly. Here's the most recent JWST observations. And the way these, so there's actually two observations here. One's observation here and the other observation there. And so when you put it all together, in the inside, you're looking at a place where there's young stars and cepheids. And so here's a color magnitude diagram for this inner region here. And Cepheids appear up here in the color magnitude diagram. And if you do this analysis that Adam has done, you get this beautiful color magnitude relationship for Cepheids. He has a couple of epochs, I guess. No, there's two right here. And using those two epochs, he can resolve some of the phase information because the periods of all these Cepheids were already known from earlier observations. And he's getting this beautiful relationship for Cepheids with scatter. Well, that would get a scatter is about 0.2, wherever that is, where does it say? 0.17, which would mean with 100 of these things that you'd be getting, you could use this to get a distance of approaching 1%. And so what he's actually doing though is he's saying, well, we know what the distance is from the bases. Now, out here, we look and we pick up the TRGB. The TRGB we want to be looking at old stars that are metal poor and low enough surface brightness so that there's not crowding. And so we go out to the very edges actually of this field here, and we get this color magnitude diagram. And if you we can get there's two ways we can get the tip, or people have been getting the tip. One is with a Hubble filter, where it's just looking at the rate of change in the luminosity function. That's actually not our preferred methodology. Our preferred methodology is to superimpose even thousands of stars on the galaxy and recover them in order to understand both the color and the crowding and how we can recover them as a function of their magnitudes. Anyways, so that's how we would do the final analysis, but this is still new data. And just as an example of how we'll be able to get really good distances, I'm now just bringing back this observation of the WLM galaxy, and you can see just by eye, I put it here, the relative distance of this local group galaxy, WLM, and the Maser galaxy, 4258, just by aligning the tip. Now, you do have to take into account some very small rending differences. So this isn't the final word up here, but up to a reasonable approximation, this is the case. And so you see right there the differential distance between these two galaxies. Now, something has come up recently which just astounded me because I don't know about stars, and this was just something that has come to my attention. Richard Anderson is the person that's been doing this. Here's a color magnitude relationship with oval information on the red giant branch in the Large Magellanic Cloud. And okay, here's the red RGB, but essentially all stars at the tip of the red giant branch are oscillating. I didn't know that. Okay, now I'm informed. Not only are they oscillating, they split into two period luminosity relationships. And if you look at it with spectroscopic information, you can get age estimates, and it turns out that there are these two color magnitude relationships, and the one they're called A and B, and A has typical ages of 4 gigayears, and this other has a typical age of 7 gigayears. Okay. Anyways, the tip is almost the same for each of these, giving them an absolute calibration based on the eclipsing binary distance to the LMC, which is again considered good to 1%, 49.59 kiloparsecs. That means that the brighter the tip, if you'd be measuring it, is this minus 4.025 in the HST band. And then if you just took that and the information I just showed you on the 4258 color magnitude diagram, you get a distance already of 7.69, which is 1.5% greater than the major distance. This is just to say that this 0 point calibration is still unresolved in the details, but I'm not seeing any big differences from what we've known in the past and in the distance scales that we've published in the past. So it's still a work in progress, but I'm not seeing a resolution to the Hubble tension in the 0 point. So that's the first step. As I say, it's not work that I'm doing personally. I'm just really trying to get educated on the whole thing. But stepping on to the work that our group is doing, I'll now talk about this transfer of tip of the red giant branch to surface brightness fluctuation. And that's going to happen because we have a cycle 2 HST proposal that's now acquiring data. The first 3 objects to come in out of 14 are these 3 galaxies in the Fornax cluster. The color magnitude diagrams are split into 2 parts for each of the galaxies just by looking at different parts of the different panels of the detector to show that there's consistency there. But here's our measurements then of the tip. And tentatively then, these are these distances that we're finding. For the 3 of them average, it's just over 19 megaparsecs to the Fornax cluster. The scatter here is about here's the scatter right here, 0.7 megaparsecs. And that is about the same as the depth of the Fornax cluster. And here's just one of these. I wanted to bring this up just to show you how powerful this is. This is one of those 3 galaxies, and here's something I had just shown you. And I'm over here, I'm showing a blow up of this part here. Now, this gap here from the dotted line, the black dot, well, this line down to the big red dot flashes there. That's 5% in distance. 5% in distance. I often just, you can look at this. You can see with my eye, not anything sophisticated, that you can pick off this the tip here at the level of a couple of percent. And so with our maximum likelihood procedure, we have we think we're getting things, relative way between the different galaxies, each one with uncertainties at the level of a couple of percent. Here's, again, just showing you the different, if I'm looking at 4258 and 13, one of these Fornax galaxies. So anyway, so this difference here is a factor of 2.5 in distance. And here's now where we want to make the transfer over surface brightness fluctuations. So this is actually what one of our observations looks like as projected onto this galaxy. In one camera, this is kind of a neat feature. I don't know whether this was fully thought through when they dreamed this up for JWST, but it's been very nice for us. We put one camera on the high surface brightness core of the galaxy, and here's this other camera over here, where way out here we can be measuring the tip of the red giant branch at very low surface brightness. And here's a power spectrum then that's coming for one of these galaxies in the high surface brightness area. Now, in the details of something, I think I leave this over to McKaylee to explain anything about surface brightness fluctuations. I'll take a back seat on that, but this is, we're getting beautiful data on that. So, as I say, we're going to be making 14 observations of the same kind of matter that I just showed you 3. And in fact, number 4 came in, the first galaxy in the Virgo cluster came in a few days ago, and it's now in the archive and available to us. And another one was supposed to be being observed today or yesterday. But in the end, then, we will have 14 galaxies to make this transfer between TRGB and SBF. Now, one of the big successes, in fact, with HST, and McKaylee was involved in this, is observations of early type galaxies in the Virgo cluster and Fornax cluster. And so you can see here that when you look at so this scale here is a measure of the fluctuation amplitude in the power spectrum. And here's just some color information from ground-based observations. And you can see here how the relationship between this amplitude of fluctuation with respect to color here for Fornax and for Virgo, and the offset here is just simply a consequence of the different distances of those galaxies. And if you slide one onto the other, like it's seen here, then that tells you that the difference in distance between Fornax and Virgo is this number here, 1.214, and that's quite well known then. This was a very good observation of the difference between Fornax and Virgo, so that if we use the NGC 4258 distance from the masers, which we then see from TRGB transfers to with only 3 galaxies, but Fornax distance of 19.3 megaparsecs, and then this is telling us that Virgo is about at 15.9. Okay, we're going to get truth observations on that because we're going to have about a half dozen galaxies in Virgo over the next few months. Now, so then we have been making observations then of surface brightness fluctuation with HST already. I was not involved in the initial work on this. The initial work then was just using a 0 point based on cepheids or the Spain scale, basically, as Adam Rees would tout. But again, then, this is then looking at 63 galaxies and getting surface brightness fluctuation distances as a function of the group velocities. Comes out with this number here that agrees with the population 1 ladder. But of course, we're going to want to replace all the 0 point issues. So at the end of the day, we will have a population 2 relationship here where basically the distances are recalibrated using whatever we find for the 0 point calibration. We've got another 68 galaxies we've already observed in a Hubble Space Telescope cycle 28. We're working with another SNAP proposal in cycle 31, where we've already picked up 15 or so galaxies as of today, and they're coming in nicely. And then we've got, there's another program that I'm not involved with, but it was looking at surface brightness fluctuation of galaxies that are hosting supernova. And so at the end of the day, already with Hubble Space Telescope, we will have about 200 galaxies extending out to about 100 megaparsec. And that's about as far as we can go with Hubble Space Telescope. But now with JWST, we can go much farther. Now, what we're going to want, though, is an equivalent to that plot here for HST using JWST filters. And so we have a program now that's been approved, but it's in the next JWST cycle. It'll start, I guess, in the fall, to observe about 40 galaxies in the coma cluster. Coma cluster, then all these galaxies are at the same distance with plus or minus about 1.5%. And so that'll give us the equivalent of this plot over here in JWST filters. And that's why I'm then going to call the coma cluster another Rosetta Stone, because again, we've got all these different methodologies that can be used in this, including things like fundamental plane and the TF relation, and there's 10 type 1 supernova in the coma cluster. So that's kind of another Rosetta Stone where we have a lot of different methods that are all, the cluster's only got one distance, and all these different methods should give us the same result. So that's, I'm coming to the end then, because I just want to emphasize what we've got here. So we've got right now with cycle 2 with James Webb, we've got this 0-point link through the link. Well, okay, first of all, there's the 0 point that we're hoping to get with Gaia information on the TRGB 0 point. And then that's being transferred with 14 galaxies to give us then a tight link between TRGB and SBF. Reminding you that those two methodologies are based on the same kind of physics. I mean, they are based on old stars that have reached the tip of the red giant branch. And surface brightness fluctuation is basic. We're looking at stars where there's very little contamination on the red giant branch. Old, abundantly, most of the population is 10 gig years or more older. The asymptotic giant branch isn't very important, and the tip is well defined. These fluctuations are well defined by the tip. Okay, so then these observations in cycle 3 that we will make of coma cluster galaxies will really give convincing evidence of what the scattering is in the SBF. And so that, and it'll give us the color relation. And then hopefully, and this is in the future, then we will then be using SBF for galaxies across the sky at larger redshifts going out to 0.07 or so. Maybe if we didn't get 100 or so scattered around the sky, then we will really nail the Hubble constant. And we'll also nail things like, is the universe actually, are there any anomalies, bulk flow anomalies, or is the Hubble constant really the same in all directions? Anyways, I'm going to argue that this population 2 procedure is better than population 1. I've been working with supernova, and there's a lot of uncertainties with type 1 supernova. We don't know how they're made, actually, and there are differences between different supernova, and you need an awful lot of information in both spectra and chemical information to do any better than 7% on a given supernova. Yeah, we think we can do 5% with surface brightness fluctuations with JWST. And here's a really important thing. We're using the same telescopes the same filters in all parts of the sky. This, with supernova, different people are observing north and south, different observatories. The data is always different. This has been done one telescope, one set of filters all over the sky, and I think that that's going to be a real winner. And that's why I say, come back in a few years, and this will be the gold standard. Okay, thanks.
Thank you, Brent. That was brilliant. Please ask your questions. Also, people attending remotely, if you have questions, unmute your microphone and just ask.
By the way, I didn't show Gabriella's.
Yeah. That's. May I?
Yeah.
Here. That's it, right? Okay, let me.
So
Where is it? Here we go. Maybe the colors. Yeah. That's the methodology.
well, this. I was just showing this today. This is the calibration the empirical calibration on this the solid line here, but this is a theoretical dependencies that come up in the color relationship in the JWST filters. So you don't have anything more to say about this, but the bottom line here is that there's really good agreement between the theory and what we're empirically finding with these 0-point calibrations right now. Okay, so
There is a question from remote. Nandini, unmute yourself and ask a question.
Yes, can you hear me?
Works.
Hi, Brent.
We can
Sorry
hear
for
you.
not being there in person. This is
See.
Nandini. Does that work?
Go on.
Can you hear me now?
Yeah.
Okay. Hi, Brent. Sorry for not being there in person. I just wanted to ask you, what do you expect to find with respect to the Hubble tension using this new set of calibrators? I mean, what's your expectation in terms of the result that we'll find?
well, okay. These new observations, I guess the ones that you're really talking about now is just with respect to the link between TRGB and SBF. I really can't address the link between parallaxes and TRGB with any clarity right now, although talking to people, I'm finding that we seem to be doing pretty good. But I'll leave that alone and say that you can see that if I've got 14 cases, and in each case, I think that we're making a relative measurement at the level of, let's say, 3%. You're going to take square root of 14 and divide that into 3%. You can see you're down there at 7.5 or something.
Okay. I have a question from SKA. Since we have lots of people involved in the engineering part of that telescope, and we want also to do some science. So you mentioned that the Rosetta Stone galaxy 4258, it's one case we have.
Yeah.
Do you know if there are expectations that we might have more with SKA, with
Well, I can't be too optimistic. Because people have already been looking. SKA will give you more distant things, but you want something pretty good nearby. The brilliant thing about 4258 is it's 7 megaparsecs. The next one we know about is 30 or something like that. Certainly, if it's anything as close as that, we'd know about it. And for 50, we'd know about it. So SKA will just give us possibilities in a regime where there has to be big errors anyway.
Okay.
Yeah.
Okay, good. Oscar, please.
Thank you. Thank you for this talk. Very interesting. And I have a comment rather than a question concerning the calibration you have shown of the RGB tip in the Magellanic Clouds. No, could you show the slide?
Oh, let's see. Okay.
If anyway, my comment is concerning the different in brightness of the two sequence A and B. No, the old one with 6 dot something gigahertz compared to the 3 point dot something.
Yeah.
Probably this difference could be due to the different core mass that star attains, that star reach when they are close to the RGB tip. In the sense that the younger sequence is made by star with larger mass but smaller core mass, so that the tip should be expected to be fainter than the older one. And I don't know if quantitatively this may explain this difference that you found, and but it could be interesting to check it, I think.
Yes. Now this has only become, I've only become aware of this in the last month or so. And so I have a lot to learn. And I mean, I don't really know about the physics of RGB stars. I think this is going to be very intriguing to follow this up.
Yeah.
Yeah. I'm not really able to comment on it except to say, wow, this is really something that's probably can be exploited. For example, when we're looking at, we're doing Gaia photometry of stars in the Milky Way. And if we do have period information, we'd be able to identify these stars up at the tip just from the period information. So we've got a lot to learn.
Yeah. Yeah. Thank you.
Other questions?
Well, maybe a question. You say you use the tip method and SBF method, right?
Yeah.
And just a comment. Both of these methods rely on RGB because they. So if there is something, it's just a provocation, not real, something that we don't know, or there is a systematic in our knowledge in the RGB itself.
Yeah.
Then this is propagating in the same way in both the methods. So maybe you need a third one.
1 and 2.
Yeah, RGB and the tip and SBF. Maybe you need a third one to be sure to be free of these possible systematics.
Well, yes, there could be systematics. I guess what I'm hopeful for is that we have these, I mean, any systematics in the population 2 group are not necessarily the same as systematics in the population 1 cepheid group. Each could be vulnerable to systematics. That's yeah. But if on the other end of the day, they actually are giving the same results, we might have some confidence. The other aspect, of course, is that there's all sorts of linkages along the way. 4258 was one kind of linkage, but in the Virgo cluster, in the Coma cluster, in all of the other clusters, the cluster has one distance, and all of these methodologies should be giving the same distance, and if they're not, we have a problem. Now, if they all give the same distance, it isn't 100% guarantee that we're right. but will feel a lot better than if we only have one method.
That's true.
Yeah.
I have one last question, and actually a comment and a question. So one comment is that with the TRGB distance available for a couple of galaxies we have to go from previous data, John lately has already checked
Yeah.
if there is good coherence between the cepheid calibration and the TRGB, but that's that's very preliminary, and they seem to align.
Yeah.
But obviously we'll have plenty of data to robustly confirm that. But my question is this: you have also done pretty much a lot of work on cosmic flows. Now, my question is, is that what happens to the local universe and the cosmic flows that we measure when you use H0 67? Does it work?
Oh, no. If you use 67, use my data with the calibrations that I got here, but you say, okay, Hubble constant 67, and I figure out peculiar velocities based on that. Then there's a big outflow. There's a big outflow. Yeah. In other words, another way of, so with flows, you're making measurements that are independent of the Hubble constant, but if you select the Hubble constant, then it's too low, then you get a big outflow. If I put it too high, I have a big inflow. So I want around 75. Sorry. Oh. $75.
Okay.
And you don't have much outflow or inflow.
Okay.
Yeah.
So if there are no other questions here or from remote, let's thank again. And